Welcome back to my channel. Dear student, today I am going to cover the topic testing of material. How we test the material? There are two main category of material testing. One is destructive testing. Second one is non-destructive testing. The type of destructive tests used in engineering are tensile test, hardness test, toughness test, creep test, and fatigue test. These are the tests which are normally performed by using universal testing machine, tensometer, hardness by Rockwell, Bernal, Beaker hardness tester, Mohs hardness scale. Toughness test is performed by using impact testing machine. Next one is the creep test and fatigue test. The type of non-destructive tests used in engineering are visual inspection, dye penetrant test, magnetic particle test, eddy current test, ultrasonic test, X-ray test. By visual inspection, we can see there is a porous structure, there is any crack in the structure. So from the naked eyes, we can see all the things. From the dye penetrant test, we use dye and penny put on the surface of the workpiece, and then we can test whether is a surface irregularities or not. Then magnetic particle test, ultrasonic test, X-ray is used for testing the crystal structure. I have made a separate video on the test of X-ray crystal structure. Tensile testing involves the stretching of a piece of material or putting it under strain and examining how it behaves under test. The ductility of a metal can be found by tensile testing using an extensometer, which is an instrument for measuring the amount that a specimen stretches or strains during a test. The extensometer is the instrument which is used for measuring the how much stretch during the loading. These specimens may be rectangular or circular but may have a specified cross-sectional area according to the standard. They also must have punch mark a specified distant part, which is known as gauge length. This is our tensile test specimen. This is a flat test. This is a round test specimen. This is a specified gauge length. This is a cross-sectional area. This cross-sectional area is a flat. This cross-sectional area is round. This is a gauge. The test procedure. The specimen is set up in the tensile testing machine, the tensometer. One is held in vice and other in a holding system. A control load measured in Newton is applied. The amount of stretch or extension that this force caused is measured. A material that returns to its original position length has elasticity. Repeated tests are carried out, making the load greater each time. While the material under test has elasticity, the extension or stretch is directly proportional to load. This is known as Hooke's law. Metals are elastic in the early stage of tensile testing. Plastics are not. When a material fails to return to its original length, it has reached its elastic limit or limit of proportionality. After the elastic limit, the load produces much larger extensometer of the specimen. This is called plastic region. At the end of this stage, the extension is even greater and a yield point is reached. A further increase in the load causes the specimen to thin uniformly and then to neck. After necking, the specimen will break or fracture. When the fracture occurs, one side of the specimen has a rough cone cup cone shape and other has a rough cup shape. So there is a cup cone fracture. One is having rough cone and another is having rough cup shape. This is a figure. Load versus extension, elastic limit, first limit of proportionality, elastic limit, upper yield point, lower yield point, ultimate tensile strength, gauge length, increment, condition at maximum load, and count fracture. Here is a universal testing machine. This is a loading unit and this is a control unit. It is a hydraulic drive where piece is held in. There is a crosshead, upper crosshead and lower crosshead. These are the sample. During the simulation you can see how plastic strain varies and here fracture happen. Next, stress we have to calculate by the how much load you applied on the sample divided by cross sectional area. There is a two stress, engineering stress and true stress. Engineering stress is a load divided by overall cross sectional area and true stress is load divided by instantaneous cross sectional area. This is a force which applied 360 kilonewton. Bar dimension is 15 mm width and 8 mm depth. Stress is found is 3 kilonewton per mm square. This is a strain. These are the some calculation you have to do after performing the experiment on stensometer or universal testing machine. Stensometer is a mechanical drive and universal testing machine is a hydraulic drive. Extension divided by original length. The extension is the amount by which the length changes and in a tensile test the original length is the gauge length. If the bar in the previous example measured 2 meter before the force is applied and 2.05 meter when the force is applied, then the strength can be found as follows. Young modulus of elasticity. In the elastic range of a material, stress is directly proportional to strain, which is another way of stating Hooke's law. This is called Young modulus. It is represented by E and measured in kilonewton per mm square. Tensile strength is the maximum force of load in Newton applied to a specimen before it fractured divided by the original cross-sectional area. Proof stress. Some materials do not have a well-defined yield point or an indication at what stress yield occurs. To overcome this, a value of stress known as proof stress. These are some terms about the proof stress. A distance equal to 0.1% of the gauge length from the origin is located. Reading 0.1% proof stress from a force extension graph. This is a line drawn parallel to the straight part of graph from 0.1% of the 56 mm gauge length. So why this proof stress is required? Some material do not have a well-defined yield point or an indication at what stress yield occur. To overcome this, a value of stress known as proof stress is used. Reading proof stress from a stress strain curve. This is a shear testing. A shear force tends to shear the material into two parts. Shear force is used in cutting with scissor, tin snips, and a guillotine. Here shearing test load extension graph result. Very ductile material, little increase in load. Example of material is copper. This is a load versus tension curve for copper material. This is a load versus tension curve for low carbon steel. Good ductility, define elastic limit. This is a for cast iron. It is a brittle material. Here is a no plastic deformation. A small amount of elasticity, no ductility. This is a cast iron. Softened brass. Brass, very good ductility. Example of material is softened brass. Example of exam question given by load versus extension result. On 25 load, extension is that much 0.15. On 50 kilonewton load, extension is 0.20. On 180 14. This is the specimen length and diameter. Drag graph determine tensile strength determine 0.1% proof stress, Young modulus stress and strain curve. So here is the solution. You can draw by using, if the load is 25, then our elongation is 0.15. So by using the data you can plot all the value in the graph paper, and by meeting all the points you can draw the curve. Maximum load is 198 and cross sectional area is that much. Proof stress is proof load divided by CSA. Redraw the first section of load extension curve. So at what point yielding start? So here from the curve you can find out the 0.5. So these are the things you have to do in the tensile testing. Compression test you can also perform on universal testing machine. Hardness of a material. Hardness is tested by measuring the material resistance to indentation or scratching of its surface. Hardness in metal may vary or can be changed by heat treatment. By quenching, you can increase the hardness. By doing the annealing process, you can make the material soft. This is the hardness testing machine. A hard piece of metal called the indenter is pressed against the surface of the material being tested. The force used is measured and the intention caused is read directly. The softer the material, the deeper the indentation will be. There are three main types of hardness tester. This is a Rockwell hardness tester. Here is a vise which is rotatable, and on the vise you can put your sample, and indentation you can made by using the putting load. So this is a simple machine. You can find out the value HRB and HRC. If the indentation is ball type, then the reading will be HRB. If indentation is cone shape, then reading will be HRC. The Bernal test, which uses a ball indenter. The Beaker test, which uses a diamond square based pyramid indenter. The Rockwell test, which uses a steel ball for soft material and diamond cone for hard material. So these are the things. The principle of basic hardness testing machine. This is a activating lever. This is a position of indenter. This is test specimen placed here. Adjusting net is this one. Most machines in use are almost fully automatic and carry out various hardness tests. Here from here you can note down the reading. The Brenal test, indenter hardened steel or tungsten carbide ball. Procedure, ball indenter forced into the surface of the test pieces by a suitable load. Diameter of indentation is measured and converted into a Brinell hardness number. The test piece must be 8 times thicker than the depth of the impression to prevent the table of the test machine absorbing the indenting force. Use on iron casting and drop forging. Disadvantage cannot be used on thin material specimen. Ball deforms with very hard material specimen. Ball indents too much with soft material specimen. This is a Bernal test procedure. Diameter of indentation measured. Ball indenter test specimen. Downward force is applied. The beaker hardness test indenter diamond square base pyramid point angle of 136 degree. Procedure diamond indenter force into the surface of material being tested, making a square shape impression. The diamond pyramid is less likely to distort under high forces than the steel ball. The diagonal length of the impression is measured and this measurement is converted into a beaker hardness number. The test must be 5 times thicker than the depth of penetration required. Used for very hard material give a more accurate reading than Brenal. Easier to use, a smoother surface is required on test pieces, which makes this method ideal for finished component. Point angle 136 degree. This is a impression which made on the workpiece. Beaker hardness tester is used for micro hardness and it is used for hard material. Rockwell hardness test. The two most common indenter are ball and cone. Similar to beaker hardness, Rockwell system has a large range of hardness scale. Each scale has its own type and size of indenter as well as a specified indenting force. C scale indicates that a cone was used and B scale indicates that a ball was used. The ball is used for soft material and cone is used for hard material. Both Bernal and Beaker hardness tests measure the surface area that the indenter make to determine the hardness number, but the Rockwell test measure how far the indenter move into the material being tested. So Bernal and Beaker measure the surface area and Rockwell will measure the depth. Next is the toughness testing. Here is a BU impact tester machine. Toughness testing can also be called impact testing or notched bar testing. The two common methods of impact testing are ISO test and Charpy test. Diagram of impact testing machine. Procedure: notched specimens are held in a vise and are struck by a weighted pendulum. The energy absorbed in breaking the test piece is measured and a value for toughness is given. The height that pendulum swings to after breaking the specimen indicates how much energy was absorbed. The ISO test specimen is held vertically, notch is facing the pendulum, striking energy of 167 joule. I for ISO and the specimen stand in the vise like an eye. This is a specimen. Here hammer strikes. This is a notch where due to stress concentration material will break. The Charpy specimen is held horizontally. Notch is facing away from the pendulum. Striking energy of 300 joule greater than I joule because the pendulum is released from a higher position. A different striker is fitted for this test. A knife edge striker. It is the Charpy test simply supported beam. Knife edge striker strike and break the machine. Next property is the creep and fatigue. Creep is continuous slow deformation over time in material subjected to steady persistent stress. In general, the higher the melting point of a metal, the higher its resistance to creep. If a bait is suspended by a copper wire, over time the wire will stand or stretch. This is an example of creep. During creep testing, specimens are held at a constant temperature under stress for a long period of time. Factors that affect creep in metals are length of time, size of load, and temperature. Fatigue: a material may become fatigued after it has been subjected to many small and alternating stress over a period of time. Fatigue may start as a little crack on the surface of the component. Slowly the crack increases and moves across the section of the component until it fractures. Fatigue testing is often carried out by means of the cantilever beam test. Hardness is a test of material resistance to indentation or scratching of its surface. Ductility: a material is to be ductile when it can permanently stretch without fracture by a tensile force. Malleability: this is when a material can be extended in all directions without rupture by rolling or hammering. Toughness: a material displays this property when it can withstand a blow or an impact. The amount of energy that it takes to fracture a material is an indication of its toughness. This is opposite to toughness. A brittle material can easily fracture by an impact. Elasticity: when a material returns to its original shape after being released from a force that was distorting it, it is said to have good elasticity. This is opposite of elasticity, plasticity. This property allows a material to be permanently deformed. Non-destructive testing: as I have earlier said, the type of non-destructive test used in engineering are visual inspection, dye penetrant test, magnetic particle test, eddy current test, ultrasonic test, X-ray test. This testing does not damage the material or the component being tested or impair its intended use. The components are first produced and then tested. Surface flaws and internal flaws can be detected. Ideal for quality control and random sampling, can be completed on site. Detection of surface flaws. Visual inspection: cheapest and simplest technique in detecting surface flaws. Good light is essential and usually some form of magnification is used. A disadvantage is that even with magnification of up to 5 times, some surface flaws may not be noticed. Dye penetrant test. Color dye is applied to surface and allowed to penetrate into any surface flaws by means of capillary action. The excess liquid is bathed off the surface after a sufficient time has elapsed. The surface is then examined under a light. A white light is used when a color dye is used. An ultraviolet light is used when a fluorescent dye is being used. Thermal testing: these are based on the high thermal conductivity of metal. Any flaw present will affect the heat transfer in the metal being tested and is shown up by the use of heat sensitive coating. Below the surface detection. Magnetic method of testing: in ferromagnetic material, cracks and cavities cause distortion in magnetic field set up in component under test. There are variations of these tests: magnetic particle method, eddy current testing. Magnetic particle testing can detect surface flaws or flaws very near the surface. Flaws show up best when the crack flaw is at right angle to the magnetic field. Wet, dry, or fluorescent magnetic particles are applied to the surface of the component. A distorted magnetic field will be displayed if a flaw is present. Difficult to use with rough surfaces. Component must be demagnetized after testing. Flaws show up best when the cracked flaw is at right angle to the magnetic field. Wet, dry, or fluorescent magnetic particles are applied to the surface of the component. A distorted magnetic field will be displayed if a fly is present. Difficult to use with rough surfaces. Component must be demagnetized after testing. Ultrasonic testing. This type of testing involves the use of a quartz crystal to generate high frequency sound vibration. A probe containing the quartz crystal is passed over the test piece. The vibrations are reflected back by the lower surface of the material and are recorded by a receiver. In most modern testing devices, the quartz crystal acts as both the transmitter and receiver. ED current testing can detect surface flaws or flaws very near the surface, used widely for non-ferrous metal, mainly for bars of uniform section. Uses electromagnetic energy detect defects in a component. An AC induction coil is used to produce ED current in the metal under test. ED currents are secondary currents induced in a conductor. These currents produce a magnetic field in the component. The magnetic field in the test piece and that in the coil opposes one another and causes changes in the current flow in the coil. All current changes are displayed on an oscilloscope. The crystal converts the pulses and echoes into an electrical signal which is amplified and displayed on the cathode ray tube. Ultrasonic testing is a rapid method of non-destructive method and can be used to test most material and in great depth. 10 meter or more for steel, used in the fishing industry to detect the depth of water and for locating fish, used in engineering for the testing and inspection of the belts. X-ray testing can penetrate metal which earthly light will not. An X-ray tube emits ray of radiation which pass through the component. These rays from an image on photographic film behind the component. A fault will be displayed on this film and it will have absorbed less radiation. It is displayed by a darker image on the film. X-ray used for NANDT are more dangerous than those used in medicine, so great care must be taken to shield from stray radiation. This type of testing is used simply for testing of belts. That's all about dear friends.